Welcome friends to my YouTube channel. Now on my last lecture I have told about the work energy conservation and about conservative forces, and from there I also told about the energy conservation theorem. Okay, now in today's lecture I shall going to discuss few other conservation theorems. Okay, so let's start. The first issue of today's lecture is the linear momentum conservation. Linear momentum conservation. This is also another conservation theorem. Now, how we can show it? From Newton's second law, we already know this force is nothing but the rate of change of linear momentum. Now, if we make F equals to 0, then this term is 0. Okay, so for a single particle, first we assume for a single particle, okay, if externally applied force is 0, if externally applied force is 0, then what we write? We write dp dt equals to 0, which implies p is constant. Okay, so this is the simple theorem, and for a single particle, that if the externally applied force is 0, then the corresponding linear momentum of the particle remains constant. So this is the linear momentum conservation theorem. Okay, so here we take a single particle system. Now if we take a system of particles, that means there are many particles in the system. Now let us explain this theorem for system of particles. Okay, now for a system of particles, for a system of particles, if we do it now, obviously in this case what happens, that is, if we consider p be the total linear momentum of the system, then obviously we can write it the sum of the linear momentum of individual particles, that we obviously write. Okay, so if we consider system of particles, then what would be the total linear momentum? The sum of the linear momentum of the individual particles. Fine. Okay, now if we make differentiation, then what we get? dp dt, this is simply dp1 dt plus dp2 dt plus dp3 dt plus dot dot dot. This is simply f1, this is f2, this is f3 dot dot dot. Here f1 includes the f1 means the total force acting on the particle. Okay, f2 the total force acting on the particle 2, f3 total force acting on particle 3. Now every force that is f1 or f2 or f3, there are two terms. Okay, so f1 can be written as f1 external, this is externally applied force, that is the force that we have applied from outside, plus the internal forces. That means f1, there are two parts of f1. One is external, that is that we apply from outside, and another is internal. Okay, similarly there are two parts of f2, externally applied, that is f2 external, this is simply f2 internal. Okay, similarly in this case there is f3 external, there is f3 internal. Okay, Now what we know from Newton's law, according to Newton's law, the internal forces always cancels each other. That means this term will vanishes. Okay. From Newton's law, what we get? The internal forces always cancels each other. Okay, so there only remain the externally applied forces. Okay, so according to Newton's law, the internal forces cancel each other. That is on sorry, that is only external forces are effective. External forces are effective. Okay, so what we get? We can write the previous expression as F1 external, that is only external terms are remained. F2 external, this is simply F3 external. So this can be written as F external. Okay. So this can be written as F external. Now if the externally applied force is 0, then this term is constant. So the linear momentum is constant. Okay. So if the externally applied force is 0, then the total linear momentum of system of particles remains constant. Okay. So this is the linear momentum conservation theorem for a system of particles. Okay. So this is the linear momentum conservation theorem for a system of particles. Okay. So if the externally applied force is 0, okay, then total linear momentum of system of particles remains constant. Okay, if the externally applied force is 0, then the total linear momentum of system of particles remains constant. So this is called linear momentum conservation theorem. This is called linear momentum conservation theorem. Okay. So this is the first issue of our today's class. Okay, that is the linear momentum conservation theorem. Now let us move to another issue, that is the angular momentum conservation theorem. Okay, let us move to another issue, that is the angular momentum conservation theorem. Okay, angular momentum. Now before starting the angular momentum conservation theorem, we have to know the connection between torque and angular momentum. Okay, now we all know that angular momentum is r cross p, moment of linear momentum. Fine. So if you differentiate this with respect to t, so dl dt, this is simply a cross db dt plus dA dt cross b, vector formula, dA dt cross b. So this is simply force, this dr dt is v and peak means mv. So this term cancels, so this is simply r cross f. So this is tau. Okay, so tau is nothing but dl dt. Okay, so dl dt, this is simply tau. So this is the relation between torque and angular momentum. Okay, so if the externally applied torque is 0, then the corresponding linear momentum is constant. Okay, so for a single particle, if the externally applied torque is 0, then the corresponding angular momentum remains conserved or constant. Okay, so this is what about the angular momentum conservation theorem. Obviously, for a single particle, that is externally applied torque is 0, this means the corresponding angular momentum is constant. Okay, now let us check what happens. Let us check what happens in case of a system of particles. Okay, what happens in case of a system of particles. So for system of particles, for a system of particles, obviously L, this can be written as sum over of I. If there are n particles in a system, then this is simply Ri cross Pi. Okay, for n particles, that we can write. So if we take differentiation, that is dl dt, this is simply sum Ri cross dpi dt plus dri dt cross pi. Okay, Ri cross dpi dt plus dri dt cross pi. So this is simply what? This is Ri, this is Fi, okay, and this is Vi, and this is Mi Vi. So this term becomes 0, only remains this term, summation of Ri cross Fi. Now what you can write Fi? Total force acting on the ith particle. So it also consists of two parts. One is externally applied force and another is internal forces. So you can write this is simply Fi external plus Fi internal. Fine. And there is a summation, that means for all particles we consider. Okay, that is for a system of particles. Now again from Newton's law, what we know, the internal forces cancels each other. Okay, so according to Newton's law, the internal forces cancels each other, that is dl dt Ri cross, the internal Fi internal becomes 0, so this is become Fi external. Okay, so this is what? This means tau external, total external torque, because here the force is externally applied, so the corresponding torque will also be externally applied, and since there are summation for all particles, this is the total torque. So if the externally applied torque is 0, if the externally applied torque is 0, then total angular momentum of system of particles remains constant. Okay. If the externally applied torque is 0, then total angular momentum of system of particles remains constant, and this is known as the angular momentum conservation theorem. Okay. So these are the two theorems. Now one thing I must have to know, what is homogeneity and isotropy, these two terms. You must have to know what is homogeneity. Homogeneity is what? Homogeneity means each point in the space is equivalent to all other points. All points are same. That is, each point is equivalent to all other points in space. Okay. So it leads to the conservation of linear momentum. This is a very important MCQ question which is asked in examinations, that which one is responsible for the conservation of linear momentum, or homogeneity of space leads to the conservation of following. You must have to know that homogeneity of space leads to the conservation of linear momentum. Okay. Each point is equivalent to all other points. That means all are same. Okay. Now another thing that you have to know, that is isotropy. Similarly, this is each direction. Isotropy means each direction is equivalent to all other directions. Okay. And it leads to the conservation of angular momentum. So each direction is equivalent to all other directions in space, or it leads to the conservation of angular momentum. Okay. So this is what about homogeneity and isotropy that I forgot to tell previously. Okay. So this is the case, that homogeneity of space is leads to the conservation of linear momentum, and isotropy of space leads to the conservation of angular momentum. Okay. So in our today's class I have told about the linear and angular momentum conservation theorems and homogeneity and isotropy, and in our next class I will tell about few other issues related to this chapter. Okay. So if you like this video, then kindly share and subscribe my channel to get more latest videos. Okay. The link of this video will be given in the description box, and if you have any query, then just write it in comment section. Okay. Thank you.